Good evening to you all. I'm glad to be with you again for the second lecture on a series of three lectures named Back to Fundamentals attached to structural design. And the topic of my talk today is about performance objectives in structural design. This lecture will be given with my colleague, Jean-Philippe Jasinski, that will take the screen for the second part of this lecture. So the focus of the lecture of last week was on graphic statics and its special significance for structural design. And today we will use the principle of plastic theorem to make a link with graphic statics for design purposes. This will lead us to discuss a series of topics. The first will be the two theorems of plastic design. Then we will be discussing option in structural modeling, strength modeling, optimum in structural design. Then I will pass the word to my colleague Jean-Philippe, who will be introducing 3D graphic statics and the use of VGS, the vector-based graphic statics tool, for several purposes linked to optimum in design. So let's start with the two theorems of plastic design. This story starts in 1914. We are in Hungary with Kaczynski that tried in a lab to reproduce the behavior of a steel column supposed to be embedded at both ends. And so the idea was to show how the elastic theory could be validated with some tests, and it could not reproduce the elastic behavior, and collapse could not be predicted. But bending, it could show that bending moment tend to equilibrate during this test. So the next step in this story was John Baker in England that was commissioned by the British steel industry. At that time, there were several kinds of elastic approaches to assess the behavior of structure. And a question that was asked to John Baker was, what is the good elastic approach to calculate the structure? And it could show that there were no elastic calculations that were able to assess the collapse behavior, and that more investigation were needed about the plastic behavior. So you will see in the next year, for instance, with Blaish, that will be investigating the calculation of statically indeterminate system based on the theory of plasticity that has been published in the IAPS Congress in 1936. And a series of work will be conducted in that way. The next chapter is in Russia, where Gvozdev in 1938 will propose a theory of plastic calculation. He will discuss this in a conference in 1936, and his colleague Feinberg, again in Russian, will publish this proposal for plastic modeling that he has been developing with Gvozdev. So these are the first proposal for plastic design, and we'll have to wait for Greenberg and Prager in the US to demonstrate these two theorems that will take the name of static theorem and kinematic theorem. So we have two theorems I will be presenting in the following slides. And in 1950, Horn will be publishing and establishing that these two theorems give the same answer when you are precisely at the state of collapse. So if you are looking to this timeline that you know already, we have seen it already for arch theory and for collapse and equilibrium theory. Beam's theory is new about this. You see that, again, this is Da Vinci proposing at the end of the 15th century the first researches on beams, and that Galilei, more than 100 years later, and Hooke and Bernoulli Euler will propose some contribution, and we arrive in 1826 with Navier here, proposing the theory of elasticity. There will be some development that will be coming some later on, and this will be still the most advanced in theory of the very beginning of the 20th century. What about the plastic theory here below? You see that the first approach are at the very beginning of the 20th century and getting a result only in 1950. So it's quite a recent approach in theory. But this was used in an intuitive way by different designers along times, and that makes something very interesting about this. Plastic theory applied to material that are supposed to develop certain capacities in terms of plasticity or ductility. And for instance, here you have the strain stress diagram that is shown for steel. You see that you have an elastic zone in blue and a red zone that is supposed to show what is the plastic deformation. Of course, this deformation is limited, and you have sometimes a conventional limit that will be proposed, for instance, to 1% for steel. What about the context of applying this theorem of plastic design? You are supposed to use normally a perfect plastic material. It means that as soon as you left the elastic zone, you are on a zone in which you have plastic deformation, and the force is maintained in the structure, whatever would be the deformation. And that's very important. It means that with such a material, you just have to wait that the system can reorganize itself to reach an equilibrium, a state in equilibrium that will be guaranteeing that it can support loadings. And since this zone is supposed to be infinite, you can also, neglecting the third zone of the elastic zone, just having a rigid plastic solution. What's the connection with the true material? You see that this plastic zone is limited, so you will need to be close at some extent to elastic behavior. And if you are not doing in that way, you will to suffer cracks or large deformation in your system before the loading could be sustained. Even for a material like masonry, when you have a typical rigid resistant in compression and no resistant in tension, as soon as you have a kind of processing that could be supported by the role and the use of the self-tway, you will have something that could be very close to the rigid plastic deformation. So you can apply also the plastic theory to materials that are not that are fragile material, that have no ductility at all. So what are these two theorems? The first theorem would say that the solution, the limit load that you will be obtaining with a loadful solution of internal forces will give you a result that will be less or equal to the actual limit load of a system. So it will providing you a lower bound to the failure loads of a system. And the meaning is that as soon as you are developing a design under cover of plastic analysis, you will be able to provide a safe solution, and that's the point. Of course, kinematic or the collapse mechanism won't be correct for this approach, but you have a lower bound result for this. It means also that whatever the approach will be using to design or dimension your structure, if your structure is dimensioned accordingly your principle, you will get a safe theorem. And this will be true regardless of what would be the actual structural mechanism. So your calculation could be different to what's happening really, as soon as you can subscribe yourself in this theorem, and guaranteeing that you have sufficient capacity for redistributing forces. What about the kinematic theorem? The kinematic theorem will on this side providing an upper bound, so an upper limit for the resistance that is of no utility at all if this is not connected with the first theorem. So it means that yield connection can be violated in this case, and it makes the theorem very dangerous. But if you are getting these two solutions together, you have here in the second column the static solution, and you have the kinematic solution in the last column. You'll see the static solution is satisfying equilibrium and yield condition, providing a lower bound. That the kinematic solution will be guaranteeing equilibrium, and mechanism solution provide you an upper bound. And if you are able to find two mechanisms that are providing the same solution, you will get a complete solution, so the actual solution. So kinematic solution will be option in which we have to navigate to find the minimum, and static solution will give you always good solution, but if you want the actual breaking loads, you will be close to the kinematic solution. So what's the application of this? This is, for instance, a lower bound approach, a safe approach that has been proposed by Méry in 1840. We discussed this last week. And this is about the kinematic solution that are upper bound, unsafe theory. And both will be converging when you will have the thrust line from the static solution that will be touching the limit of the system, providing the hinges that you see appearing here, and that gives you the opportunity to give an actual precise solution for this analysis. So what you are looking is this solution in between, but relying only on the static solution, you will be able to guarantee some result. What's about this? Is I'm moving to a portal frame, for instance. Here I am developing just one approaches, and if I'm dimensioning this portal frame according to the system I developed, you will get the actual, the real solution. If you are, so this is on the state of design. If you are moving on the state of analysis, you have to put forward different hypotheses, and you don't know at the beginning what would be the maximum, but it's what you are looking for. But in any case, if you are not finding the right maximal solution, you can find a temporary solution in which you are able to guarantee at least a resistance of the structure. So that's for the elastic, for the analysis on the side of the equilibrium theorem. If you go to the plastic theorem, you see that when you are reaching limit of elasticity somewhere, we will be developing hinges. And in this case, you will see hypothesis in which you are developing hinges in several places, and you are just assessing what would be the possible solution, and the minimum will be corresponding to the limit. So that's a connection, and both together, you will have the final solution that will be provided. So having this, and there will be connection to graphic statics, of course, I will be discussing. So let's moving to the option for structural modeling. I'm not about the structural design. I'm just for modeling. As we have seen, you can put forward several solutions. If you're looking on a beam, you can model it either as a truss, this is a truss analogy, or either with the classical analytical bending approach that would be followed. The fact is that for several materials, as for reinforced concrete, for instance, this approach below cannot help you to assess what would be the resistance in shear forces, not assessing the resistance, but calculating what would be the reinforcement you have to implement in your system with the spacing of stirrups and the actual resistance of struts into it. So the same problem can be represented in very several ways. Of course, you can make connection with graphic statics, as you know, and you can find the associated mechanism to this, and you can combine also in between model on side of truss or of truss line or even something else. You can multiply model, as in this case, for finite structure or tree branching system that will all enable you to assess your system. And if I stand to this is, for instance, this system of the finite system that will be used most of the time when you are working on assessing shear walls on concrete structure with the system of the Studentine modeling. You will have different results. And of course, this result will show you different forces according to the modeling you will be using. And that could represent a kind of question tag, something that is not straightforward, but you see option even in modeling several problems. At the end, what would be the objective could be using stress field and student time modeling, as in this example that will be discussed later after introducing what is stress field and student time modeling. So let's move to the next chapter. You know, maybe this model that is used for calculating shear forces and reinforcement against shear in concrete structure. The story starts actually with William Ritter and Emil Mauch at the very beginning of the 20th century. And from this, there will be two parallel developments that will be made. The School of Zurich and Copenhagen with Drucker, Nielsen, Thürlimann, and Whitney that will first focus on stress field, and from them developing the corresponding student time modeling at the collapse state. That's important. So we have in plastic zone, and the School of Stuttgart with Leonhardt and Walter, Rusch, Kupfer, and Sledge that will be focusing to a state close to the elastic state. So that we start from the elastic analysis and not from the collapse mechanism to put forward several student time modeling in what they call D regions. So D regions are the detail region where you have connection, varying section, high beam, or shear wall. We have not the possibility to use the classical theory of elasticity, as I will be showing, so you have to go somewhere else. By extension, if you can use a strut model or a truss model for a beam, why are you using truss on one side for the shear forces and bending on the other side for calculating bending forces? You can use only one model, and this is what we'll be about in the next slide. Just for presenting student time modeling, if you have a simple column, you will just have a strut running into it in blue. But as soon as you have a shear walls, you will see a kind of spreading of forces, a bulking of forces, in which you will see as a stress field, this is an elastic stress field, you will see a tension trajectory appearing perpendicularly to the compression forces. And this will be the resulting student time model showing that you have compression in one direction with a bulking and tension in the perpendicular direction. So that's typical for assessing concrete shear walls. So the approach followed by the School of Stuttgart is first seeing that you have no linear system, so you cannot apply the theory of elastic behavior. And for this, you will be drawing the elastic stress field. You see compression direction in blue, trajectories, and red trajectories below, and you will replacing the red in the second step with tension bars made of steel. So that this is what is made here with a strut system replacing all the trajectories in blues, and the red trajectory that will be the tie that you have to provide to your system to sustain forces. Of course, you can use vectorial analysis for this with graphic statistics, but the School of Stuttgart don't do it. But the School of Zurich, well, and going back to the School of Zurich, you can see here a kind of kinematic approach based on the lab. You see the pattern of cracks appearing in a shear wall, and from this you will be able to develop the compression stress field, the mixed zone, and multi-axial stress field, and the tie appearing here with a special zone below. And when you have to define what will be the forces that will be met, you will translate this to a classical student tie model. Of course, this model can be differently if we're just punctual forces that will be applied to the system, you will have prismatic stress field. And what is shown with this sharp limit is that you have rigid plastic behavior here in a plastic zone with full deformation and activation, and here you are not in the rigid zone in which you are not activated to the diagram. So there's a direct connection with what we have seen just before. If you know this Brazilian test on the cylinder to demonstrate what would be the tension resistance of concrete, you will see appearing in the middle, in the perpendicular direction to the strut, in this direction, we see appearing tension forces. And indeed, you have this spreading, this bulking I was mentioning just before with tension and trajectory forces. And you can simplify it with the classical 32-degree angle that model a system. And here we have the full modeling system with graphic static demonstrating the compression trajectories as struts and the tension trajectories as ties. Going back to this, normally you have to consider along the strut the same mechanism, and you have to implement this bulking. And depending on the place where are your limits, you will be developing student time modeling in this case. So this is the simple and this is the detailed system. This shows you that you have to take into consideration compression and tension perpendicularly to it. And at the end, you will have kind of rules for dimensioning this. Ties will just be the steel. You have struts in the transverse direction that will be under tension force. And struts, depending on the level of cracking you have in your system, will be in between 0.6 and the full compression force. And you can also have confinement properties with the lateral force that could be applied to the system. So typically for sheet board will be between 1 and 0.8 times the value of the characteristic resistance for design. Of course, we have to analyze nodes according to several topology, but I don't have time to discuss this in detail. At URF, you are able to model the behavior of any system using strut and ties, and from this you will be able to assess them using very simple vectorial analysis, and that's the point of our lecture today. Here we have several examples of using student time modeling, and you can apply it also to other mechanisms. For instance, you have here student tie system into shear walls made of CLT panel. On the left, we have the fan-like approach that I was putting forward just before. On the right, you have the integral approach in which you have you can see the truss line approaches. That is a kind of generalization of the fan-like system. And with this, you can analyze quite complex system for which we have no simple mechanism coming from the classical approaches from the elastic theory. So this application is developing a system of student ties. So this is an application of the lower bound theorem, the static theorem of plastic design. So we are projecting a system into it for the analysis, and that make all this interesting. Here we have a more detailed example coming from Buitoni, Schwarz, and Turliman as published in 1996, in which we have the first sketch about the stress field and about the corresponding student tie model with the analysis that could be made classical or using graphic statics with a force polygon. And at the end, they will give you mechanisms that could be calculated in a very similar way that you are calculating here a shear force into the structure. So these are for more basis we need to develop structural system, and we will go to the question to optimum and structural design. So the first point, of course, we have to question is what would be the mechanism you can develop in several systems in between traction and compression, or just compression, depending on the material. For instance, concrete alone without reinforcement, it's just about compression. And you have to go to several systems that will be suited for this. And you have a whole range of available systems. And you have to develop for this several systems, for instance, here as tree structure. Keeping in mind that your system just finding plan won't be stable and that you have develop your system in several directions, for instance, in 3D, as you can see here, and hence the interest of 3D graphic statics, of course. But you can also add supplement several systems just to assess your system, and you have the wide range of possibility that could be coming from this approach, with a possible exercise in optimizing the detail of this, for instance, for the inclination of the struts into a truss system, for instance. If you want to discuss optimum, you have first to scan what could be the solution you want to put forward. For instance, you can assess the global amount of material, or if you want to minimize the number of joints that are costly, or if you want to minimize the number of joints by nodes, by connection, since it will make your connection more simple and it will lower the price. You can go to limiting the length of some bar in compression, for instance, to avoid buckling. You want maybe to control the magnitude of forces when you have the geometry that will be interacting with this. For instance, if you have very sharp angles between two bars or almost right angles, it won't spread the force very efficiently into the vertical or horizontal direction. You can go to constant force geometry. You can try to rationalize typology to have constant or minimal section for families, or take this question for families to analyze the connections instead of the bars. You can combine several materials, and depending on the problem, some material would be the optimum or not. You can also assess the way that you want connecting several elements, for instance, horizontal and vertical bars in the portal frame system. And with embedding or not at a connection, you can foster some specific working. For instance, you want to foster tension for steel or foster compression for concrete as it will not crack. So you have a whole range of possible approach that you have to cross with the possible geometry that you have to develop in your system. Of course, graphic statics can help you to assess what would be the solution with constant force system. As an example here, that's a very classical example. You will have constant force in the blue vertical line and the horizontal black line, but not in a red one. And below, this will be the red and the blue one that will be optimized using graphic statics in this case. And if you want to assess what could be an optimum, I presented a series of a parameter that could be considered. You have to add also the question of cost, the question of constructive optimum, and you have to interact also with the notion of environmental assessment. And you know that, for instance, for several materials as timber, you will have negative global warming potential. If you have to compare with steel or with concrete, it won't give you no result at all. So this series of optimal approach have to interact with the question of the modeling in the middle, and at the end with the question with the structural types that is not just an image of the modeling. So it drives the problem of optimum very complex, and what you need is a need for control for all this. And the approach we decided to follow in the team about all this was connected with a visual representation of graphic statics, either in 2D or in 3D dimension. Since 2D have been developed last week, we're moving now to the 3D graphic statics, and I will giving the screen to my colleague Jean-Philippe Jasinski.
Thank you very much, Denis, for the first part of the lecture. Okay, so I will follow with the part 2, which is about three-dimensional vector-based graphic statics. So maybe just a smaller word of introduction. So my name is Jean-Philippe Jazienski. I'm a researcher at UC Louvain Structures and Technologies Lab, which is run by Denise Astavny. I've been researching on the topic of 3D graphic statics for more than 10 years now. And what I'm going to present to all of you today is actually the fruit of a very nice collaboration with various people from different universities. So we have people from the TU München, from ETH Zurich, from EPFL Lausanne, and also from Southeast University Nanjing. And so all together we work on this topic to collaborate and make it nicer advances. So the plan of the second part of the talk of today is as follows. So it's divided in 5 parts. First, I will introduce the context. So why shall we have a look at structural design in 3 dimensions? Afterwards, we'll discuss the various approaches to 3-dimensional graphic statics. I will discuss the vector-based approach, which is the one we work on, but it's not the only one. And the other approaches have also their own benefits. So that is something that we'll discuss in the second part. Then afterwards, I will explain the theoretical framework behind vector-based graphic statics. Which means that we will discuss precisely how to build the diagrams, so really the theory behind it. Then the 4th part will be about the computational implementation of this theory. So we developed a tool, a computational tool that is called VGS, and I will explain to you how the theory goes into this tool and how it works and what are the possibilities of it and what will be the next development. So after that, we'll finish with some case studies. And so we'll show different examples of case studies that were developed with VGS tool and 3D graphic statics. So the context, okay. So structural design in 3 dimensions. I hope, okay, it doesn't go automatically to the next slide. What is a typical design process between architects and structural engineers? So basically the way it typically works is that architects will come up with sketches with very nice architectural ideas that can be even more crazy now, since we have all these nice computer-aided tools such as Rhino, Grasshopper, and all these very nice tools. We can come up with very strong and very diverse and sometimes very complex architectural ideas. And so the plan is to go and see the structural engineer and work together so that it stands and it makes a building. So the problem is that sometimes what we do as architects is not fully meeting what it could be as a structure. And so the tools that are available now to the structural engineers are mostly FEM, optimization, form finding. There are many nice tools, but most of the time you have this back and forth loop because we come with an idea, we check, does it work? It doesn't work. We have to change a little bit, adapt, and then maybe this calls for an important modification of the architectural concept, and then we modify again. And then this loop, in the end, when the project is more or less finished, there could be an implementation, some details and construction. Sometimes this process, which is kind of the typical process, what I mean by typical is that it's not the only one, obviously, but it's something that is really common in practice. The problem is that sometimes some extreme examples like this one that you obviously know, the Walt Disney Concert Hall from Hungary, which is an interesting project. But I mean, you are coming with maybe a bit crazy idea or innovative, let's say, and then after you have to convert that idea into a building. And so when you have a look at how much structure you need, which kind of details you need, I mean, that's something that you can question yourself about. Is it really such a strong project if you need so much material for it? And so you obviously all know that we live in a context in which the resources are at stake. So we would like to decarbonate the world, decarbonate the industry. And so if you have a look at the embodied carbon assessment in buildings, you can see that actually the structure and the construction is really the main part. I mean, superstructure 42%, 13% substructure. So that really means that there is a huge potential to optimize and to develop together with the architects some buildings that are more efficient as structures. So that's really something we cannot not look at, you know. So I kind of like this example because the small history behind it, it's that this paper was presented in 2014 in Brasilia, Brazil, at the IESS conference, and the researcher Catherine de Wolf, who is now a professor at ETH Zurich, she decided to analyze different stadiums because it was at the time of the World Cup in Brazil. And so that was a bit an important topic at the moment. We were the year of the World Cup. And so she made a paper with Jonas Sundorf and Ogroyan G from MIT both about the material quantities and the embodied carbon in stadia. And so we have, I've chosen just 3 examples from her paper. So on the left, you have the London Olympic Stadium, so the Millennium Stadium from 2011. In the middle, Brazilian Stadium, the João Havelange Olympic Stadium. And on the right, the Beijing Olympic Stadium for 2008, which is known as the Nest. And so these stadiums, among others, were compared in terms of material quantities and embodied carbon. So this is more or less like the final figure of the paper. So the 3 that I've shown you is the Millennium Stadium. So the first one here, the João Havelange, which is the 3rd one, and the Beijing Olympic Stadium. And so here you have the resulting kilos of CO2 by seat, obviously. Since they don't have exactly the same size, the idea was to bring them by seat. Also, we can think that most of the stadiums were not really done in the last years in which we really start looking a lot at this thing. But I mean, it's impressive to see that I think the 3 projects are interesting at some point, but it's impressive to see that the Beijing Olympic Stadium needs more than 10 times the material, the kilos of CO2, but obviously this is in relation with how much material you place compared to the London Olympic Stadium, which is a really slender and thin structure. So at some point, it is normal that from a project to another, you don't have the same values, but nowadays in 2023, is it acceptable to reach the same goals in terms of program and use more than 10 times the resources in a world in which we know that and the resources are limited? And so the big question behind it is what is the relationship between architecture goals and structure? I mean, can we keep on thinking that it's 2 different things? that first the architect work, and then we make it feasible, we make it stand, we make it as a structural designer something that can be built, or does it have to be something that we develop together, like a collaboration from the beginning? And so if it's like this, which tools can we use to have a common dialogue between architects and engineers? So the big question is, what is the relationship between a shape and the forces, the inner stresses, the forces that are acting on the structure that it needs to take? And so I kind of like this example that I guess probably most of you know. So this is an abstract from the book on growth and form from Darcy Thompson. So that's a book from the 1955. And so I kind of like it because Darcy Thompson was not a structural engineer. He was actually more of into biology and what we call mathematical biology. So the central thesis in his work is that biological forms, so more or less everything that exists in the world and that is natural, so animals, but also trees, vegetables, everything. So the central hypothesis is that these biological forms are not arbitrary, but rather the result of physical and mathematical principles. So he argues that these principles can be understood and analyzed using mathematical tools such as geometry, mechanics, physics. Okay, so throughout the book, he has chosen a wide range of examples from the natural world to illustrate his ideas. The form of animals, plants, shells, and showing how they can be analyzed and understood in terms of mathematical principles. So in this example, you can see two bones. On the right is a femur bone, and the line is are actually stress lines. So he was really into understanding compression traction as well, but understanding how the shape of your femur is actually in relation with the fact that it needs to transmit the weight of your upper body to your lower body. So the shape is not arbitrary. It's in relation with the forces that are acting on it, with the constraints. On the left is a crane head bone, and it's the same. So it's just a small example that is not related directly to structure, but I think it's a great inspiration of how we could think about designing buildings and structures. So obviously, I'm not the like inventor of this idea. Many interesting designers already discussed that idea. So I will have a look at this citation from Eladio Dieste in 1996. So the resistant virtues of the structure that we seek depend on their form. It is through their form that they are stable, not because of an awkward accumulation of material. So there is nothing more noble and elegant from an initial viewpoint than this, to resist through form. So a first example of one of Eladio Dieste's building, it's a plant for packing citrical fruits, such as lemons and stuff. And so you can see that the structure of the roof is one thing. The way the light enters, the space is defined, the way it spans the whole space without columns. It's architecture and structure is one project. It's not two ideas that need to collaborate. It's really like an integrated approach. He was obviously not the only one to produce magnificent buildings such as this one. I showed just one example from Candela, in which also the relationship with space, structure, light, construction, it's one integrated approach. And so if we have a look at the design methods, I just quickly do a small link to something that was already well explained in the lecture last week by Denis Zastavny. So the Salgy-Natobel bridge, which is really a benchmark of structural efficiency, was achieved using 2D graphic statics. So you've seen this working drawing in which on the left, you have the form diagram, and on the right, you have the force diagram. And so you can really directly and visually understand the relation between a form and forces. And so Denis Zastavny with Corentin Fivet, they did a very interesting paper about the Salgy-Natobel in 2012, and they explained how the material was used in relationship with the form of the bridge. There was a real optimization so that the thrust line and the centroids of the sections were trying to be as close as possible. So removing this material makes that the centroids are lower and almost aligned to the thrust line, so that the material that is in the bridge is used without creating important bending moments, and really trying to achieve as much compression as possible. So all the material that is used in a nice way, in a nice from a structural point of view. And compression is probably the most efficient way to carry loads to the ground. Maybe a few things about these 2D graphics statics examples is that the result is a sustainable, efficient structure. The calculations were not so complex. Actually, if you have a look at Maillard's calculation, it's not 2,000 pages of calculation. Some bridges is very, very short. That's almost frightening at some point. But the way he managed to impose himself as a bridge designer was in the end because he was saving materials. So the costs also were quite low. And so the idea of this introduction is to discuss the difference between structural engineering, which is about analyzing forces, and structural design, which is about designing with the forces. And obviously, structural engineering is important, and we don't say that FEM is bad and that you should not use it, because you will always at some point use it for things, just that maybe in the first step of a design process, it's not so easy because it's mostly about analyzing, not real-time design. So now if we have a look at the question of 3 dimensions, like complex 3D shapes, we can have a bit of look at the historical examples so that we can see what was done before. Obviously, models were important. For example, these examples from Heinz Hissler and the shells that were built that were amazing structures, very slender, very nice. The work of Gaudi was also inspirational in this term with his hanging model that he was done. You obviously, I guess, know them, but he did these hanging models, and then he would build it on the rivers, so reversing traction and compression. So this is the Colonia Güell. So models were really a tool to design complex 3D structures. We can also use 2D graphic statics and twist it a little bit so that it becomes 3D, such as in these examples in which you can see that you have a wall, another wall, and then you have a point where the force travel to the supports. And so that's a way a little bit to use 3D with 2D diagrams that you would assemble together. And so this is a built example using these principles. So it's from Christian Karetz and Joseph Schwartz. So it's a building of different apartments in Zurich. And you can see that the walls are not aligned. So it's really this concept that the forces travel through the walls that are considered with Strut-and-tie models. And so you can really at some point free the facade. And that's a very interesting built example. So why shall we do 3D graphic statics? Maybe a second and the last citation of the presentation of today from Alan and Zalewski. So graphical methods contribute to intuitive understanding and visualization of behavior. They greatly facilitate all statistical operations. In early stages of design, they have significant advantages over numerical methods in their simplicity, speed, transparency, and ability to generate efficient forms for cables, arches, trusses, and other structural devices. So the idea of doing 3D graphic statics is to deal with this relation between shape and forces. So the goals, the objectives are the following ones. First, we would like to have an intuitive and direct understanding and control of the flow of forces through the structure. Then, thanks to that, we could tackle 3D structures that are complex, because obviously for many examples, you can use 2D graphic statics and use it as a section, do a section in one direction, the other. So, I mean, 3D graphic statics would be more interesting when the geometry becomes complex and cannot be treated with 2D graphic statics, which is already a very powerful tool. So with 3D graphic statics, you have a mix of traction and compression elements. So you don't need to have specific hypotheses on material before dealing with that. And that's an important point compared with FEM models, with which you need to already define the elastic behavior of your materials. And the idea is that you can use it as well for structural design, but also for analysis. And Denis showed you in the first lecture that in terms of analysis, the thrust line, masonry, arches, buildings, graphic statics can prove a very valuable tool. So we arrived to this topic of 3D graphic statics, and we can discuss the various approaches. So basically, nowadays, there are two main approaches that derive from first theories from the 19th century, and we classify them as the polyhedron-based approach and the vector-based approach. So let me explain this page to you because it's quite important. So on the left, you have a form diagram, okay? So our convention is blue compression, red tension. This you already see in Denis' presentation. So basically, this is pushing the blue parts, and you have some cables in red, some tension elements, okay? And from that, you need to do a force diagram, okay? So this is the structure. As you can see, it is a self-stressed structure. So you impose compression in one of the bars, and all the structure is then self-stressed. And so in the polyhedron-based diagram, one node corresponds to one face of the polyhedron, okay? So you can see V1 correspond to this face. V4, the node, correspond to this face. And so what it means is that the intensity of the forces is the area of the face. There is something very strong with this approach, is that these two diagrams are reciprocal. It means that to one node correspond one face, okay, and vice versa. In this case, in the vector-based diagram, one element correspond to, so one element here, okay, like this compression bar, correspond to one or two elements in the force diagram. In this case, this is the element, you can see they are parallel, and the intensity of the force is the length of the vector, okay? So there is one big point that we will discuss in detail today, is that these two diagrams, they are interdependent. So if you move one thing in one, it will affect the other and vice versa, but they are not reciprocal, because in the middle here, you have this line and this line, they are actually the same elements here. So one element can be represented more than one time. So it means that you have non-overlapping vectors. It's the same for this one and this one that correspond to this one. And so they cannot overlap. And I will explain after in detail. So basically the main benefit from the polyhedron-based approach is that the diagrams are purely reciprocal. And I would say that the main benefit from the vector-based approach is that we believe that lines are more easy to perceive than areas and volume. If you have a look at the literature, so this reference is from McKinley, he classified visual elements, okay, such as position of element, length, angle, slope, area, volume, density, and how accurate the human can perceive these elements. And you can see that lines and lengths are from the more accurate elements that you can perceive. Volumes and area are a bit less accurate to perceive. So we decided to work with the vector-based approach because even though it's not reciprocal, we believe that it's quite visual at some point. So if you have a look at this small example, for example, this branch of this branch structure, the intensity of the force is this phase, okay? If we have a look at a similar example, so you have a tree structure, and so if you take a small branch of these three branches go in this, okay? And so you can exactly, so it's, if we have a look, this one is parallel to this one, and so these three small forces, the resulting is that, and it's this line. And then if you take this one, this one, this one together, so it's 1, 2, 3. And so this big line takes exactly the resulting of these three forces. And so that corresponds to that. And if you want to have a look at this vertical element, it's this length. So at some point, we believe that the strength of the vector-based approach is the visual convenience and the readability of the diagrams, okay? But both approaches are very interesting and have their own benefits, and I really strongly believe that it's very nice that different groups develop different approaches, because all of this at some point is making the topic of 3D graphic statics stronger, and this is what we all want, that graphic statics is more used by designers, by architects, by structural engineers. And so all these approaches at some point are not fighting against each other, but they are complementary. And so if we have a quick look at the computational implementation of these approaches, you can see the Polyframe tool from a polyhedral structural lab from UPenn. So this is developed by Masoud Akbarzadeh and his colleague Andrei. And it's a very nice and powerful tool. And Masoud will give, I think, 2 lectures in the scope of this Digital Future seminar, and he will explain that in detail, and you will see that it's very, very strong and very nice. You can download it. I put the link here on Food for Rhino. Then obviously Block Research Group with Philip Block and Tom Van Meel, they developed with Johnny Lee, among others, the Compass 3GS or PGS, so polyhedral 3D graphic statics, which is another tool that does polyhedral 3D graphic statics, so polyhedron based. So that's also something that is very, very strong. Then there is a tool that exists already for a few years online on Food for Rhino, and that is quite used, and it's called 3D Graphic Statics, and it's developed by Ongjen Raovac. Maybe too small information on this tool is that it's working with compression on structures, and it's using the algorithms and the theory developed by PSL, so UPenn and BRG, so Block Research Group. Obviously, the small question is RhinoVolt, because it's a very powerful and very used tool. So RhinoVolt, even Philip Block himself considered it to be 2.5D, which means that at some point, the resolution is thanks to a projection of a 3D structure that you project, and then you solve on a plane the force diagram. It's a very powerful tool. We used it with our students during many years and had a great result. And the version 2 is even stronger. So that's also something very interesting, very nice. And this one works with vector, but it's working with projections. You can see that the force diagrams are flat, okay? And so this is bringing some kind of limitations. And the tool that we developed, which is VGS, is with vectors, so vector-based graphic statics. On the left, you see the form diagram. On the right, the force diagram, okay, of a bridge with a compression deck and two compression pylons. And here it's the force diagram, and so you can very easily read the force in all the deck members here on the right, okay, corresponding to that. One pylon, the other pylon, corresponding to the four external forces that are doing like 1, 2, 3, 4, and that they close with the small red forces corresponding to the angles. Okay, this we will discuss more afterwards. So we arrive to the third part. So we introduce the context of three-dimensional structural design. We discuss the different approaches to three-dimensional graphic statics, mostly the polyhedron and the vector-based approaches. And now I will explain the theory behind vector-based graphic statics. So this part will be a bit more mathematical, let's say, or a bit more theoretical. So I hope it's not too boring. Okay, so let's jump back to where we were. So form diagram on the left, force diagram on the right, okay? The idea is, how can we produce a force diagram ourselves? If I just give you Rhino, how do you deal with that? What is the construction, the geometrical construction to build a vector-based force diagram? So first of all, when you have external forces, you need to solve the external equilibrium. So we developed a paper on that was published in 2016 at the IESS symposium in Tokyo. And so what we explain in detail is what is the geometrical construction that you need to do with sets of planes to find the resultant of all these green forces that are skewed, so they are not meeting in one point in space. And what is the geometrical construction that you need to do to close them and find the resultant? So on the right, you have the force diagram. On the left, you have the form diagram. The geometrical construction is explained quite in detail in the paper. I will not go too much in detail, but basically you have to build successive planes and find some meeting line between the planes. What I will discuss a little bit in detail, because that's really the base of everything that I will explain you afterwards, is how to solve the equilibrium of one node. Okay, so you have one force acting and three elements. They all connect at the point P0. And you want to know what is the intensity of every force that is there. So basically, it's quite easy to solve. You have to think that we started working on this topic 10 years ago. And before we had all these tools, computational tools, we did a lot of graphical construction ourselves, like as I will explain to you now, because it was the only way we could solve it. So basically, how does it work? You have to build planes with two elements, and then the two following ones, and then the two following ones. So let's have a look. The first plane, okay, that we see here, P1, is the plane defined by the line F20 and the line F10. Okay, so if you take two lines in space, you can build a plane. Okay, so we build a plane with these two lines. We choose whatever plane point on that plane as a starting point. Okay, so here the first point would be O1. And then we have one plane, one point, and we know that F10 will be on this line. Okay. And then we build a second plane which is P2 with F20 that was already in P1 and F30. Okay. And then we place this plane, and with the meeting of the planes, actually, it will define the length of the elements, and we can close the cycle. Okay, and so for this node, you know that the length of F10, it's the magnitude of the force, the length of F20, F30, and the resulting F00. Okay, so that was also something that we developed in detail in another paper that we did for the 2016 symposium. And so now we know how to solve a node. Then we will solve the nodes of all the structure and think about how can we assemble them together to have a complete and closed force diagram. Okay, so here it's the form diagram. And here it's a topological diagram. So you just project it, draw it. Actually, in a topological diagram, the length and the angle of the line don't matter. It's the connectivity that matters. Why do we do that? To provide an order, a sequence after for the assembly. So first, we will solve this node. Okay. And so we close one by one. And we use a clockwise order on the topological diagram. And so we close this. So exactly as I explained to you, the same construction that you can do geometrically or that you can also solve algebraically. And then you do the same for node B, respecting the clockwise order that is indicated in the topological diagram. That is our help to have a rule for the assembly of the cycle of forces, and so on. And so we solve all the nodes of the structure, okay? And so the question is, from all these nodes, how can we make them together, how to assemble them so that we have one force diagram, okay? Something like this. You see all these nodes together, this node that was here, you can see it there. Okay, so how can we do that? What is the rule that we can use? And so to do that, we will use the topological diagram. And I don't know if you know a little bit about graph theory, but I will do a very small recap. So as you can see, this topological diagram is not planar. What does it mean? Diagram is not planar when you have crossings. Okay, you can see that F6 and F4, they are crossing in this point. Okay, and you can move the points wherever you want, you will always have a crossing. This is because this diagram is not planar. So the strategy to have a way to assemble the force diagram is to planarize this graph, which means adding nodes. And this is where we have the nodes that in the end, we will have non-overlapping bars. So if I add a node here, okay, then F6 and F4, they are split in two elements, and that's why they will be represented twice. So this node here, which is like a fake node, a node that we added for planarization purpose, is here. You can see F6, F6, F4, F4. Okay, so that's there. And you will tell me, yeah, but there are many ways to planarize the graph. You did it like this, but I can move the nodes and do it another way. And the answer is yes. You have many different possibilities to planarize the graph. So that is leading to different force diagrams. So since it's not a pure reciprocity, the solution is multiple, which is also interesting because we will discuss it afterwards, but you could generate different solutions for the same structure. So this is another example. So you see all the nodes where you see that the letter change. So we manipulate the diagram and planarize it differently. And so the answer is another force diagram. In this case, it's F5 and F3 where we add one node. And so this is the corresponding quad, as we call it, or where you have two pairs of non-overlapping vectors. Okay. If we have a look in 3D, this is it. Okay, so this is in the VGS tool, and here we already show how we can transform one diagram or the other. But that's just a small teaser. Okay, so you can really see in 3D that you have these nodes. So a small recap of what we did. We have a three-dimensional form diagram. Okay. We draw the topological diagram, then we planarize it. So this is already a planarized version of the topology. We have all the cycles of the form diagram, and thanks to the information we have in the planarized topological graph, we can assemble together into being one three-dimensional force diagram. So the theoretical rule is very simple. You can decide to split whatever edge of the topological diagram, as long as when you split it, you add a node. Okay, so this is what we did in this example here. F6, we split it in two elements, and F4, we split it in two elements, and we reconnect them to this new node. So this is the general rule of the theoretical foundation. We did a journal paper on that explains the theory behind it in a very more precise way than what I'm doing now as a summary. And so I invite you to read about it if you're interested. So this is the example we've just seen. This example, I placed it just to explain how does it work with external forces. When you have external forces, so you can see that this is a net made of traction cables, okay, in tension, all of them, and with all the green external forces. And so something that we added is that the external forces, they all connect to what we call VE, so the vertex of the external forces. And that's the way to be able after to planarize it and generate the force diagram. In this case, the diagram was already planar, so these two figures are reciprocal, but this is not the general case. So after you have your force diagram, you want to transform it to achieve specific geometry, modify the structure according to constraints. You want more height in one space or another space to be wider, or modify the forces to be aligned, to be smaller. And so this is one family of transformations that you can do which are global transformation, such as scaling in 1, 2, 3 directions, skewing elements, okay? But you can also do local transformation. So you take one node, you modify it, and then the force diagram will be affected, okay? So these are the two family of transformations that you can do. Now we'll just quickly have a look at an interesting property of 3D vector-based graphic statics that also exists in polyhedral graphic statics. It's the subdivision of elements. So you have on the right one single node and the force diagram, okay? And so from the force diagram, you can actually do a geometrical construction with planes to build a new substructure. Okay, so you first build 3 planes, then connecting lines at the nodes, and then you have these new intersection lines that appear, and that makes it a substructure of that. Okay, and then you can keep on. You do exactly the same construction for this node here. You can see that you can identify them all the time because you have this pair of non-overlapping vectors there, then it's there. Okay, and so at some point you have a force diagram that is interesting because it has different levels of hierarchy. And so this is the final result. So you can see that the initial force diagram that was here, you can still read it. It's still there. And you have all these different levels that you can see in the structure. Okay, so this is one of the different properties of 3D vector-based graphic statics that I wanted to highlight today. So as a conclusion to the theoretical part of the presentation, when you have form and force diagram in 3D, you can use different sets of transformations to achieve a specific goal. So this is one of the case studies that I will explain in detail to you at the end of the presentation. And as you can see, you can deform it to attain specific goals and generate the structure that you want to create. So now we enter the fourth part, in which we will discuss the computational implementation of the theory that we've just discussed before. So maybe a small introduction to the design and development team of VGS, the Grasshopper plugin. So it's a collaboration between 4 people, 4 friends actually: Pierluigi D'Acunto from TUM, Yushi Shen from Southeast University in Nanjing, Patrick Ole-Holbrook from ETH Zurich, and TUM, and myself. So we worked on that for quite a long time. Actually, it was more of a tool for our own research. And since this year, now it's available for free, the beta version, the version 1 that is stable, is available for free, and you can download it at this link and use it to build very nice 2D and 3D vector-based force diagrams. So I will very quickly explain how we converted the theory into a tool. It's kind of interesting to know how it works, so that when you use it, you have a knowledge and understanding of how it works. So first thing first, you need to define your structural model. So to define the structural model, you need a geometry and forces. And with forces, we have as well supports, obviously, to support the structure. But if it's self-stressed, then you don't have external forces. So basically, with your forces and your geometry, you can generate a form diagram F. Okay? And at the same time, you can see that this arrow divides into two procedures are carried. On one hand, the equilibrium solver that is integrated into VGS will determine the intensity of all the forces in the structures, so all the force intensities, okay? But it's quite important to know that this is not mandatory to use our solver. Actually, you can provide the equilibrium from whatever other source, CEM being one of them, but you could use other tools such as Caramba, such as other tools, and just provide the equilibrium to VGS. In the meantime, there will be the quest for the assembly sequence that you can see here. So for that, we'll use this module that looks for the assembly sequence, so what we call the sequence finder. And this will planarize the topological graph and provide an assembly sequence. For that, you can choose among different algorithms that were developed. So there is a choice by the user. I will quickly present 3 of them today, even though in the beta version, there is only one that is integrated. But the idea is to be able to generate different kind of force diagrams from that. And so with these 2 information together, so you have an assembly sequence and the force intensities, you can use the assembling procedure, which travels all the nodes to assemble them one by one and be sure that it all connects to have one full force diagram. When you have your force diagram that corresponds to your form diagram, you can then transform it. Thanks to Kangaroo, the numerical solver that we implemented into VGS, you can apply some goals, some constraints, and modify the 2 diagrams accordingly. So even though the diagrams are not reciprocal to each other, they are interdependent, which means that if you modify one, you will in real time assess the difference, the modification in the other one. And so you have these 2 diagrams that are connected by the transformation. Okay, so now we'll see a small video that highlights VGS. So the video outlines the structure of VGS, which is structured in 3 parts. So first, equilibrium, then transformation, then visualization. So, as you can see, VGS will provide a form diagram first, and then with the matrix, generate an equilibrium solution. As you can see, other tools such as CEM, force density method, finite elements, and other things could provide the equilibrium as well. So with that, we have form diagram and force intensities. Then we need the planar graph. And for that, VGS allows you to do it manually or do it automatically using the algorithms that were presented. And with this information together, we have a form and a force diagram that are interdependent. So to each node of the form diagram corresponds one cycle in the force diagram. And then we plug them together in the transformation module that relies on Kangaroo. And we can apply geometric constraints and goals and transform them and directly see how the transformation affects the forces and the form. So you can apply constraints such as geometrical constraint, but also numerical constraints, such as I don't want that to be that element to have a force higher than X kilonewton, for example. So these 3 parts together allows the designer to have a full integrated approach that allows him to control the flow of forces in the early stages of design. So it's really a complete workflow that can be used for design and analysis. So on this slide, what we can see is for planarizing procedure. First, the general procedure, that is the one that I introduced in the theoretical part. This is what we call the by-hand procedure. Basically, the by-hand procedure, the solution can be any solution, since while you respect the principle that I explained, meaning that whatever edge can be split and reconnected to one or more newly introduced vertices, while this condition is fulfilled, then you can produce whatever solution. So all the solutions from the algorithm could be also solution from the by-hand procedure, because with the by-hand procedure, it's the general procedure. Then we see the cycle algorithm, the quad algorithm, and the med algorithm. Basically, quad and med belong to the same family. They are incremental algorithms, which means that they will start from a reduced planar graph that we call the maximal planar graph, and then add elements one by one, elements that they will split until we have all the elements that are added back to this maximal planar graph, and then you have the full topological graph that you can see here or here to assemble a structure. On the contrary, the cycle algorithm works with removing elements or splitting elements. So it's a bit closer to the general procedure. So it looks for the elements that are not that are producing non-planarity and then splits them. So it's quad and med work as incremental procedure, and cycle works the other way around. So basically, we can see two different solutions, the cycle algorithm. And so what happens is that F is converted into T, a topological graph, and then the algorithm looks for what we call the Kuratowski subgraph. What is the Kuratowski subgraph? It's a subgraph, so a part of the full graph that is non-planar. And this subgraph will provide us some information about the edges that we could split so that little by little we achieve planarity. You will tell me, but you don't have so many elements in that, such as in this figure. And the answer is yes, all the dotted lines actually contain different elements. So that was done for computational purposes, because you can store information in matrices and stuff, in lists. And so basically, when it's dotted, it means that it's corresponding to more than one vector. And so you have the force diagram here and the force diagram here. So it's two different ways to planarize. Then you have the quad algorithm, which is quite important to know because it's the one that is now implemented in the better version 1 of VGS computational tool. So basically, I would say the main principle is that when there is a crossing, it adds a node, as you can see. Okay. You have two different results corresponding to how you generated your maximal planar graph, which was a reduced version of the topological graph. And the MED, the MED algorithm, which works differently. It doesn't work with adding nodes, but sorry. The MED works with visiting the vertices. So for example, if there was one line going from V1 to V4, it will replace it by a line that travels to V4. So that will be one line, another, and another. Or V1 to V4 could be this one, done. And so that's why you don't have, that's why you have more edges and you don't have so many nodes as in the quad, because it works in this way. Okay, so these are the three main algorithms that were developed, but at this point, only the quad is included. So if we have a look at the full definition, first you have your form diagram, then your force diagram, then the transformation, the settings for the transformation, okay? And then how you visualize the results and how you can analyze them. This is like a typical VGS definition. So now we'll go through different examples. This one that I already showed you. So this is where you start using the transformation. You are skewing the bridge. Okay. So you go from 2D to 3D. And then you can apply other constraints. This example is also an arch bridge. So it's not a suspended bridge, but you have this compression arch on top and this compression deck here. And as you can see, you can freely modify. You have the forces on the right, on the left, and the form on the right, and you can see that you can really modify them. This is another example of bridge with 2 compression arches and 1 tensile member on top, and the force diagram on the left, on the right. Sorry. Okay, so you can define nodes, and you can see that you can play with the forces, play with the geometry. And very quickly, it's crazy how you can really modify the design and go to another solution. Okay, this is another example in which you just modify the way you have some self-stress in it and how you go from traction to compression. And so how you go from shell to how you go from shell to a cable net. Okay, so now we'll have a look at another way to use VGS. The idea is that I told you, you can provide the equilibrium from different sources, which are, for example, algebraic solver, which is into VGS, but force density method, CEM, and so on. But there is also a way to use VGS without calculating the force diagram and generating it directly. So on the left, you have a first geometry that you defined, and you will ask VGS through the aid of the numerical solver Kangaroo to modify the geometry until it finds a force diagram that closes, which means that all the cycles are connected to each other. And so we'll see some examples. So this is a tensegrity structure that I would like to do. So I quickly draw some members in tension and some other in compression, and then I ask VGS to generate the force diagram. Let's see if it converges. Okay. Then you can see the solution, and you have on the left your form diagram, and on the right your force diagram. Okay. We have another example after that. This is something we've been working on with Professor Denisa Stavny. This is Piper Marienkirche, and you have one arch and another that connect to each other. And so basically what we've drawn is a stupid geometry here, because we know that VGS will modify it until it finds a suitable solution. So I launch it because it's quite a long process, but so as you can see, we also impose some specific geometrical conditions, such as this resultant has to be vertical. And you can see that little by little, it's converging until these lines that connect the two force diagram, the one of one arch and the other, is getting vertical. You know that generating funicular structure is not such an easy task to do it manually. And so in this way, the way we are using VGS can really provide you geometrical solutions such as funicular structures, because as you can see, our starting point was not funicular at all. We just did two triangles And then the result, as you can see, it's quite interesting because the thrust line is inside of the arches. Okay, so that's another way to use VGS. And then it's a bit the same principle, but going to the last feature of VGS that I will show now. But basically, it's using the same algorithm, and we are getting close to Mitchell trusses. You see, it's starting to converge. And so we go to some last examples of VGS. Okay, so basically we developed a module that is not in the beta yet, but that is doing load pass optimization. And so basically it's optimizing the load pass. And so modifying the geometry little by little here, acting on the forces to get a way more optimal solution. Okay, I will show one last example of the same kind. And it's trying to converge with optimization. So obviously, all these tools, you can use them manually, but with optimization, you can really go faster and get better results. And so now I will just say a few words about CEM, which is a bit, I would say, the baby of Patrick Ole-Holbrook and Pierluigi D'Acunto. Ole developed it in his PhD at TTH, the CEM, and it proves to be a wonderful friend to VGS because CEM always provides geometries at equilibrium. So the way CEM is developed, you can plug it directly to VGS and so start with a geometry that is at equilibrium. So these two tools work very good together because VGS is really about producing the force diagrams, but sometimes starting from an equilibrium solution can be tricky, can be an issue. And so in this way, CEM proves to be a very nice addition. So I will quickly explain to you how it works. Because in the case studies, the starting point is most of the time from CEM. Basically, the way CEM works is starting with a topological diagram that you can see here below. Okay, so in the topological diagram, you define different things. First, the connectivity between the elements. Okay, so you have two kinds of way to connect elements. Here you have an external force. Here you have a support. Okay, the elements that will connect directly the external force to the support is called a train, and the train will go from the external force to the support. 1, 2, 3, 4 trains that you can identify here. External force, support. 1, 2, 3, 4 trains, okay? But then it's maybe not interesting for you that your structure is just 4 bars that go directly from the external forces to the support. So you would like to shape your space, your structure, so that it's meeting other goals. And for that, you have a second kind of elements, which are the deviation. And so, for example, this first, it's in dashed line. This first series of elements correspond to this first ring. Okay, the last one is this one. So you define connectivity, then you can choose if your elements are in tension or compression. And for the trains, you can define their length. And for the deviations, you can define the force magnitudes. And CM will always provide you with a valid result that is at equilibrium. So this is really nice because you will get an equilibrium solution and you can optimize the solution with CM so that it's getting close to what you want. But then you can also plug it into VGS to have the force diagram that corresponds to it and use the transformation module to achieve specific geometrical configuration. So a very simple series of examples. You have on top 1, 2, 3, 4, 5 different topologies, okay? And to each of these typology, you have the corresponding structure. So here, what you can see is that basically it's super simple, super straightforward. From the external force to the support, it's just a line, okay? And so you have columns, vertical columns that connects external forces to support. Then you can start playing, adding some elements in between, some deviations, and generating this structure. Then you add like rings at all the stages, compression ring that you can see here. You can start modifying the forces in the deviation, and it could be really something else. As you can see, these two topologies, we just shifted some element from tension to compression, modify the values, and you have more structure with compression core and hanging structure. And then here you can switch, as you can see, compression, tensile ring, compression ring, tensile ring, compression ring. So red, blue, and then you can start modifying the values more randomly and get other solutions. So CM is also a tool for Rhino that can be easily downloaded from the same platform, which is called Computational Structural Design. And there you can, from this repository, get the last version of CM, which is now the 2.0, okay? And so CM can be used to provide geometries for different kind of structures, or whatever kind of structures, because it's not so much related to a single solution. But here we can see a series of pedestrian bridges. This one is a suspension bridge. This one is a big compression arch with some hangers that are crossed. This one is composed of two branch structures in compression that support the deck that will have some tension in it. Here it's a flying arch, as we call it, because you have this compression arch in the middle that is really flying because it's not touching the ground. It's taken by these tensile members that will have huge forces, obviously, because we'll have to have equilibrium at these nodes. This is like a more classical 3D arch truss. And here we have, for example, compression column, a pair of compression columns and hangers. Other kind of typologies, it's a stadium design. So from the small story, we did a workshop of CM at AAG in Gothenburg in 2017. And this was the design task that was given to the students, like making a structure for a roof for the stadium. You can see that in the examples that we have, there are many stadium roofs because Ole is very interested in stadium design, has been a great footballer. And what you can see is that, for example, some of the solutions are inspired from known designers. You can see some Kenzo Tange inspiration, Calatrava, you have a bit of everything, but it's different kind of solutions for the same problem. But you can also use it for buildings. So in this example, it's for multi-stories buildings. And what you can see is that you can generate many ways to make the structure stand and to have like a clever structure that brings the loads to the ground. And it's very different kind of solutions. And as you can see, for example, For those who know the reference, this one is inspired by the Lichtenbach School from Christian Keretz and Joseph Schwartz. This is a bit more Sendai, like the Mediatek, the Sendai of Toyo Ito. This could be a bit some projects of OMA and stuff. So you can really tackle the program and generate many different solutions. So now you can see them in video in 3D if it doesn't stop. Okay. So you can see the different solutions that we So as a conclusion to this small apartheid, VGS and CM work great along together. And this is what I'm going to show you in the case studies, is that providing a geometry at equilibrium from CM is really a great first step to tackle a new design task. So I will show you a bit more in detail the case study of a stadium roof. So basically, this is the definition of the problem. We start with a stadium roof that is symmetrical, so we just designed half of the structure. We consider this to be the origin nodes, so where the forces start, and this to be the support forces. And in these points, we will impose the force to be totally horizontal, so that when you have the symmetry of the structure, you have equilibrium at the node, obviously, because you will have two facing horizontal forces from the same intensity. And so that allows you to make a symmetrical structure. Okay. You can see that the trail go from the origin to the support, and you have all the deviation. Yeah. Okay. And so this is the first iteration that you get from CEM. So the structure is composed of two compression rings that you see in blue, and then hangers that connect them together. Okay. And in green, you can see the forces that are perfectly horizontal, so that they will match to the opposite forces when we build a symmetry. What we can directly see is that here in the tensile ring, the forces are very strong compared to the two compression rings. So this is the full structure. And so when we get this result from CEM, we can plug it into VGS to have the force diagram. So this is the force diagram that is a mix of tension and compression. So since the screen is flat, it's better to see it from top and from front view. You can see that it's quite beautiful, I think. So this is the front view of the stadium, and this is the front view of the force diagram. But after that, we would like to transform them so that they meet some specific geometrical constraints and some constraints on the forces. So we will apply these constraints if my video doesn't block. Okay. So we impose that it goes to this plane so that it will perfectly match the symmetry. And then we impose that it modifies so that it connects to this guides that we place. Okay, and so the optimization process goes on until we have the full result. So we go to case study 2, which is a suspended bridge. So it starts with CEM as well. In this case, the structural concept is for a pedestrian suspension bridge. And so the deck of the bridge has to be hung below one main suspension cable on 24 secondary hangers. The deck has to be anchored on two given support points, which are separated from 80 meters. So that would be this point and this point. Okay. And the main cable should be suspended between two pylons. So it's this one and this one. Okay, so given this setup, the task is to propose an overall geometry of the bridge, considering that we predefined a uniformly distributed load on the deck of 10 Newton by meter, sorry. So the first instance of the geometry that you can see in dashed line was generated through CEM. Specifically, we modeled the upper part and the lower part as two trails that we could see here, trails and trails. Okay, and then we have this part. So we will apply a first set of geometrical transformation to make the support match the support points that are located on the sides of the river. Okay, then in the second design step, we will do a shear transformation and a non-uniform scaling along the y-axis so that we adjust the form diagram into the specific support constraints. Okay, and then in the last iteration of the design, we optimize a bit the forces, as you can see, and we convert, basically we rework this point to make it better in equilibrium. And so we convert the two pylons with two pylons and two hangers. Okay, so you see that there is a change. That was one line, okay, that corresponds to this line. That was one line that corresponds to this line. So here we divide these two elements in two, tack, 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 so that from a construction point of view, you have here one node with 4 elements. And so that makes it in equilibrium for whatever load case, because this one is a kinematic structure, meaning that it's only stable for this load case. But if you have forces that will push there, since this and this are in the same plane, it cannot be at equilibrium. Here we have like, I would say what we would call a tripod. You know, when you have 4 elements going into one node, then you can have many different possibilities to redistribute the forces. And so that's the small render that we did, maybe with pylons that are a bit too thick, but to illustrate this suspension bridge. Then I will go very quickly, because I also see that I'm reaching the end of my time, through the third case study, which was for the ISS 2016. It was a competition that was launched by the ISS to give a proposal for a fictional stadium for the Olympic Games in Tokyo 2020. And so the winning proposal was by Pierluigi D'Acunto, Lucas Ingold, and Ole Holbrook. And so this is the design that you have these compression rings that are floating and connected together with a series of hangers, which allows light and a structure that is really floating, and so light to enter the pitch in the ground. So these were some renders of the proposal that you can see. And that was it. And so I will finish my presentation with a last case study, which is basically a node, so a node of a structure connecting 6 elements. So you can see 1, 2, 3, 1, 2, 3. Okay. So the topic is the design of a connection node of this structure. At some point, it's interesting for different reasons. First, that graphic statics can be used at different scale. It's not only for the global structure, but it can only be used to design connection nodes, assembly between pieces. So it can be used, it's not scale related actually. Then what I kind of like in this example is that we use a theoretical and mathematical property of graphic static, which is the subdivision of the force diagram to generate the geometry and have an optimized repartition of forces. And then what I kind of like as well is that in this example, we generate a geometry that is optimal, but that is not so easy to build. You can see the result here. And so at some point, what is nice is that you connect it to digital fabrication to propose a solution that is more optimal than the traditional answer, but that is made possible thanks to digital construction. So in this case, you can see that through the subdivision, what we got is this same strategy of tripods. So for all the nodes, you have 1, 2, 3 supports that go to 1, 2, 3, 1, 2, 3, okay? Which makes it a bit difficult to build here in the middle if we don't use digital construction. And so the way we did it was aluminum casting into a 3D print mold that you can see here. So it's a 3D print of sand printing. In 3D, you have the different pieces of the mold. So you can assemble them obviously together. This one goes in the center, and this one, and this one. And from there on top, we casted the aluminum. And so the result was this node. And so I will use this last example to conclude my talk of today. That was the second part of the Back to Fundamentals series by Denis Zastavny. So we discussed three-dimensional structural design, and so how graphic statics in 3 dimensions can prove to be a very good ally for tackling an integrated approach for both architecture and structural needs in an integrated approach, so that they would merge in the goals, the objective, for the building, for the structure, or whatever design project, including both architectural and structural needs. And then we explain in detail the fundamentals, the theoretical foundation of vector-based graphic statics. Then we showed the computational implementation of vector-based graphic statics, which is the VGS plugin for Grasshopper. And then we finished with a few examples, a few case studies. So thank you very much for your kind attention.